Hello everyone, I am Ikra Sarfaraz working as PhD scholar at Department of Zoology, Government College University, Faisalabad. I would like to welcome you all in the AZSP first international webinar regarding World Cancer Day 2021 on behalf of the organizing committee and principal organizer of this event. The Applied Zoological Society of Pakistan is running a series of webinars and seminars regarding various health awareness days each year. AZSP aim is to make a real impact in raising awareness of health issues across the community and to bring science closer to the society. In the context of World Cancer Day, 4th February 2021, AZSP have organized this first international webinar in collaboration with Department of Zoology, Government College University, Faisalabad, with the key theme photodynamic therapy as an emerging tool in the treatment of cancer.
Thank you, Ikra, for such a nice welcome message. Now, with the recitation of Holy Quran, we would officiate our webinar. The sparkle of fire is the witness of your worth. The silent flounce of water is the witness of your rhythm. The rhythmic movement of the moon is the witness of your perfection. My words, my soul are the witness of the glorification of Allah, whose glorification cannot be described in words. For recitation of Holy Quran, I request Mr. Hafiz Arham Shehzad, BS Islamic Studies, member of Sayyid Manzoorul Quran, Qiraat and Nas Society of Government College University, Faisalabad. Please, Mr. Hafiz Arham, join us for the recitation of Holy Quran.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم إن الذين آمنوا وعملوا الصالحات كانت لهم جنات الفردوس نزلا خالدين فيها لا يبغون عنها حولا قل لو كان البحر مدادا لكلمات ربي لنفد البحر قل لو كان البحر مدادا لكلمات ربي لنفد البحر قبل أن تنفد كلمات ربي ولو جئنا بمثله مددا ولو جئنا بمثله مددا قل إنما أنا بشر مثلكم يوحى فما كان يرجو لقاء ربه فليعمل عملا صالحا ولا يشرك بعبادته ربه أحدا صدق الله العظيم.
Subhanallah, Jazakallah. Thank you, Hafiz Aram Shazad, for lighting our hearts with holy verses of Quran. Now it's time to pay homage to our last prophet, Muhammad sallallahu alaihi wasallam, the leader of all the prophets, the reason behind all the creations. I request Muhammad Jawad, General Secretary Sayyid Manzoorul Hunain, Naat and Qiraat Society of Government College University, Faisalabad, to pay a humble and melodious tribute to our last prophet, Muhammad sallallahu alaihi wasallam. Please, Muhammad Jawad, join us for Naat Mubarak.
خوشبو ہے دو عالم میں تیری اے گل چیدہ کس منہ سے بیاں ہوں تیرے اوصاف حمیدہ تجھ سا کوئی آیا ہے نہ آئے گا جہاں دیتا ہے گواہی یہی عالم کا جریدہ کس منہ سے بیاں ہوں تیرے اوصاف حمیدہ یوں دور ہوں تائب میں حریم نبوی سے सहरा में हो जेस्तर हा कोई शाख बुरीदा किस्मों से बयां हो तेरे साफ़े हमीदा
Jazakallah, Subhanallah. Thank you, Mr. Jawad, for paying such a melodious tribute to our last prophet, Muhammad sallallahu alaihi wasallam. Now, I'm highly elated to introduce our today's keynote speaker, Dr. Khetre Khorsandi, who is a faculty member and head of Department of Photodynamic Medical Laser Research Center, Yara Institute, ACCR, Tehran University of Medical Sciences, Branch, Tehran, Iran. She has PhD in biochemistry. Her research interests include photodynamic therapy, photobiomodulation, photodynamic inactivation, cancer biology, stem cell regeneration, and nanobiotechnology. Dr. Khorsandi is winner of many well-known awards, which include Young Scientist Award, ranked first in 3rd Iranian Congress of Trace Elements in Kashan, Iran, during the year 2013. She is awardee of FAOMB Young Scientist Fellowship Award from 14th FAOMB Congress, Hyderabad, India, during the year 2015, and FAOMB Young Scientist Travel Fellowship Award from 25th FAOMB Congress, Philippines, during the year 2016. Dr. Khorsandi is winner of IUB-MB Young Scientist Award from 16th IUMB Conference 2016, Vancouver, Canada, and IUB-MB Young Scientist Program Award from 24th IUB-MB Congress, Korea. She is awardee of AZSP Fellowship Award for the World Congress on Light and Life 2019 from European Society of Photobiology 2019, Barcelona, Spain. I request Dr. Khorsandi to join us and deliver her remarkable talk on photodynamic therapy, current status, and future applications in cancer treatment. Please, Dr. Khorsandi.
Hello everyone, my name is Khatere Khorsandi. I'm Assistant Professor of Biochemistry at Department of Photodynamic, Yara Institute, Tehran, Iran. I'm here to deliver a presentation about photodynamic therapy and its application in cancer treatment. So I'm gonna tell you an introduction about light and light-based therapies, then with more detail on photodynamic and its different aspects in cancer treatment. Well, let us start
as I said, my presentation is about photodynamic therapy, current status, and future application in cancer treatment. Diagnostic can be under UV, visible, or near infrared, that they are different in wavelengths, also energy, and the target that we want to use. For example, as you can see here, their penetration on tissue that can be a target for us is different. As you can see here, UV area, blue light have a small penetration, but red light and near infrared light has more penetration in tissue, and we can use them for a different target like drug release or particle targeting or so on. Among the light-based therapies, photodynamic therapy or PDT is a modern and non-invasive form of therapy used in treatment of non-oncological diseases as well as cancer of various type and location. Good therapeutic result and possibility of parallel application of PDT with other therapeutic protocol make it more commonly used in many fields of medicine, such as it's successfully used in dermatology, oncology, gynecology, or orology. As you can see here, it has three main parts, including photosynthesizer, light at specific wavelengths, and oxygen that lead to photochemical reaction that I will discuss in detail in next slide. Okay, photodynamic therapy is based on local or systemic application of a photosensitive compound that we call it photosynthesizer or PS, which is intensely accumulated in pathological tissue. As you can see here, after administration, we have accumulation of PS in a specific tissue. The photosynthesizer molecule and initiate the activation of process leading to selective destruction of inappropriate cell or tissue. So photodynamic therapy is well tolerated by patient because it's a selective action, and photodynamic protocol mainly are painless, and simplicity of their application allow for outpatient use also. Photodynamic therapy is used in treatment of chronic inflammation, and is an interesting alternative in treatment in drug-resistant bacteria infection that we call it photodynamic inactivation, PDI or APDT. So as you can see here, the concept that I said is certain photosynthesizer that we use, and activation of photosynthesizer by light that will lead to photochemical reaction. Here I want to discuss about PDT mechanism. As you can see here, molecular mechanism of PDT is based on three non-toxic compounds, as I said, including PS, light, and oxygen. There are two main mechanisms of PDT reaction. Both are closely dependent on oxygen molecules inside cell. And at the first stage of both mechanisms are similar. The photosynthesizer PS, after entering the cell, irradiated with light, then it will change, transfer from a singlet basic energy state to excited state, as you can see here. After absorbing the light, it will go to excited singlet state, and then after that, part of energy is radiated in the form of fluorescence. Then at remaining energy, direct a photosynthesizer molecule to excited triplet state. Okay. Then this excited triplet state is therapeutic form of the compound, as you can see here. After that, there is two mechanisms, type 1 and type 2 mechanism for PDT. In type 1, in the excited triplet state, a photosynthesizer can transfer energy to biomolecule which surrounded PS. Okay, then this biomolecule absorb this energy, and after absorbing the energy, lead to formation of free radical and anion radical of photosynthesizer, as you can see here, which lead to production of reactive oxygen species, initially in the form of super anion radicals, which create a generation of rust inside cell and lead to oxidative stress that finally damage the cancer cells or different microbes. In type 2 mechanism, as a result of photosynthesizer transition into excited triplet, energy is transferred directly to O2, oxygen molecule in the basic energetic state. Direct transfer between molecules is possible because they have similar, same spins. In this way, excited oxygen particle, we call it singlet oxygen, as you can see here, is extremely strong oxidizing properties that most organic compounds like And as we know, they are in basic singlet energy. However, oxygen molecules are characterized by their triplet state. And when they're excited to singlet state, they are extremely strong oxidizing properties, as I said. So it leads to damage of biomolecules such as amino acid, nucleic acid, fatty acids, and finally destroy the unwanted cell. It's assumed that mechanism of type 2 is the most important process conditioning the efficacy of PDT. Nevertheless, the ratio of contribution of both mechanisms depend on many factors, including oxygen concentration, tissue dielectric constant, and pH. Also, photosynthesizer structure. And that which kind of this compound that we use lead to type 1 or type 2 PDT mechanism. Okay, after that, highly reactive oxygen species cause photo damage of protein, as I said, lipids, other molecules in this area. They lead to direct death of tumor cell. That can be in the process of apoptotic, autophagic, necrotic. And photosynthesizer can localize in different subcell or location, and this leads to different cell death mechanisms. For example, mitochondrial or lysosomal leads to apoptotic cell, endoplasmic reticulum PS location lead to autophagy, and plasma membrane damage lead to necrotic damage. Well, I said PDT has three important parts. One part is light, and light delivery is important in PDT process. We can use different light sources such as laser or LED, but nowadays there is a smart type of light delivery such as fiber optic diffuser through skin for transdermally application, template grids with needles, or wireless power implantable LED light sources. As you can see in here, they are much smarter and smaller for use, and for the area that we cannot use the LED sources, big LED sources or laser sources, we can use this kind of light delivery. Another part is, apart from light and oxygen, is the presence of photosynthesizer. As I mentioned, PS, and these dyes are defined as substances capable of absorbing light with a specific wavelength that triggering photochemical or photophysical reaction. Okay, this kind of drug should have several characteristics such as selectivity to tumor cell, photostability, biological stability, photochemical efficacy, non-cytotoxicity in absence of light, strong absorption in IR area or near IR area, 600 to 800 nanometer, good tissue penetration, and line triplet excited state lifetime. So this most of the time these things cannot be happen and lead to challenges in PDT. Most challenges are hydrophobic characteristic of PS, that photosynthesizer penetrate the cell membrane, or under physiological condition they tend to form aggregate, and another is low selectivity of PS to the desired target. Mechanism of PDT cytotoxicity can be indirect or direct mechanism. Indirect mechanism lead to changes in tumor micro environment, antivascular effect, anti-tumor immune response. But directly lead to killing of cell, macromolecule damage by apoptosis, necrosis, or other cell death mechanism. As you can see here, in direct cytotoxicity, there is anti-tumor immune response such as release of photo-inflammatory cytokines, fixation of a complement system release of tumor-associated antigen, and in antivascular effect, we have a vessel leakage, thrombosis, and these are strongly depend on PS use and time interval between the administration of PS and light. But in direct cytotoxicity, and there is a macromolecule damage inside the cells. That this macromolecule damage occurs very close to the location of PS activation and singlet oxygen production. Different PS, as I said before, can localize in different area in cells such as plasma membrane, lysosome, mitochondria, endoplasmic reticulum, and so on. Apoptotic cell deaths tend to predominate in the most PDT sensitive cells at a low light and photosynthesizer dose, but necrotic mechanism tend to predominate at higher light and photosynthesizer doses. So the percentage of apoptosis achieved as well as the mechanism of apoptosis, it depends on tumor cell lines and photosynthesizer. In this regard, we have done different research and study in application of PDT for cancer treatment. As you can see here, I bring some of our recent research and using different, PS and different strategy for cancer treatment. I want to discuss one of them as an example that we use curcumin as a PS. And we use the nanoparticle of curcumin as a form of curcumin intercalated layer double hydroxide nanohybrid for using it against triple negative breast cancer cells. In this research, we synthesize curcumin in LDH and we characterize it, and we just find that it's a nanostructured curcumin LDH. After that, we use it against triple negative breast cancer cell lines, and we saw that in presence of light the cytotoxicity increased and also the colony formation decreased. Also we had enhancement in the apoptotic cell death type. We had cell cycle arrest and more RAS production. Also, as you can see here, the morphology of cells change to apoptotic cell deaths. We continue our study on using curcumin as photosynthesizer, and we have done several different studies such as combination of curcumin with salicylic acid, methylene blue, or using ion paired nanoparticles. Another aim of our research group is using a lower level laser irradiation for increasing anti-cancer activity of some drugs. For example, in this work, we use it for increasing the anti-cancer activity of parcumaric acid. In another work, we use it for effect of a low level laser on anti-cancer effect of gallic acid, and we found that in presence of low level laser radiation, the anti-cancer effect of gallic acid increased by RAS production, induction of apoptosis and phoroptosis, another cell death mechanism in both human breast cancer cell line and melanoma cancer cell line, but it wasn't toxic against human dermafibroblast or human non-tumorigenic breast cancer cells. Also, we have done a study about the effect of photobiomodulation on biological response of stem cells. It can be proliferation of a stem cell or their differentiation to other cells. As we know, there is some challenges in using PS and PDT, as I discussed earlier. In this regard, we know that over the last decade, a significant acceleration in development of nanotechnology has been observed. We call it nanomedicine, that use nanomaterial platform for diagnostic or therapeutic procedure, enabling the precise drug delivery to target tissue and improving the effectiveness of anti-cancer therapy. So the combination of photosynthesizer with nanomaterial can improve the photodynamic therapy efficacy and also eliminate its side effects. Also, the use of nanoparticle make it possible to achieve a target and targeted method, which is focused on a specific receptor. As a result, increase the selectivity of PDT. PS may be encapsulated, immobilized, and with different kind of interaction, covalent and non-covalent, that I will discuss in next slide. As you can see here, advantages of nanocarrier, they have a high solubility, high stability, and so on. So I said there is different strategy for incorporating PS and nanoparticle. The first one is PS contain inside self-assembled nanoparticle. As an example, liposome or micelle are in this group. Lipid-based nanoparticle. The first group is liposome. They have a simple structure, controllable size, high loading capacity, flexibility for modification. As you can see here, is the simple structure of liposome. The hydrophilic drugs or PS can be inside the liposome and hydrophobic on the outer area. So a smaller liposome exhibit more efficacy and accumulation because the large one are easily eliminated by macrophage on complement protein. Another type of interaction of PS with nanoparticle is using embedded in nanoparticle using polymeric or mesoporous silica. For example, here I show silicon nanoparticle. They prepare with well-controlled particle size. Several different PS can be encapsulated. They have non-toxic nature, inert and stable properties, potential non-reactive toward microbial or enzyme, insensitive to fluctuation in temperature and pH. Due to permeability of porous matrix of silicon nanoparticle, as you can see in here. So singlet oxygen is generated inside, can easily come out, and the photodestructive effect can be maintained in encapsulated form. In this regard, we have done a research on using curcumin silicon nanocomplex and examine its photocytotoxicity against melanoma cancer cells. In this research that we published recently, as you can see here, first we synthesized a curcumin silicon nanoparticle. We characterize it with different techniques, and we find that it's nanostructure. After that, we examined its effect and phototoxic effect against melanoma cancer cell line, also normal human dermal fibroblast cell. As you can see here, by using light, PDT process, curcumin silicon nanoparticle show better effect than curcumin alone. Also, it's non-toxic in different time against human dermal and normal fibroblast cell. We use another technique such as fluorescence microscopy. As you can see here, that apoptotic cells increase when we use curcumin nanoparticle, and then PDT, the colony formation decrease, and also the rust protection increase. We use this nanoparticle, curcumin encapsulated in silicon nanoparticle against bacteria resistance. Two bacteria we selected, Pseudomonas aerogenes and Staphylococcus aureus, as multi-track resistance bacteria, and we find that it has good photodynamic activity in destroying this bacteria in the form of planktonic and also biofilm form. Another type of interaction of PS with nanoparticle is PS can bind to the surface of nanoparticle. As an example is metal nanoparticles such as silver or gold nanoparticle. As you can see here, then the PS can just bond to the surface, and in contrast to solid nanoparticle, metallic nanoparticle can be used better because they have extremely small particle size and can have a huge surface area that can load large dose of PS. In this type of nanoparticle, also we have done research, and we use curcumin silver nanoparticle against Pseudomonas aerogenes bacteria and photodynamic inactivation. As you can see here, with using curcumin with silver nanoparticle, the photodynamic activity, antimicrobial photodynamic activity increased significantly in the planktonic form of bacteria. Also, bioformation ability decreased significantly after APDT with curcumin silver nanoparticle in compared to curcumin alone. And also, this strategy wasn't toxic against human dermal fibroblasts, as you can see here. The cell viability is almost around 80%. Okay, other type is nanoparticle themselves act as PS. In this case, the nanoparticles themselves have to be able to absorb light by virtue of possessing an excitation coefficient of appropriate size in an appropriate region of electromagnetic spectrum and to form an excited state that can lead to some photochemical generation and production of RAS. Example of this group of nanoparticles including fluorine, graphene oxide, titanium dioxide, quantum dot, and also upconversion nanoparticle that I will discuss and some of them in detail. There is just in this photo recent development of nanoparticle, as I said, that they can use themselves as a photosensitizing agent for antimicrobial PDT or PDT in cancer treatment, such as fluorine and graphene oxide nanosheet, silver nanoparticle, also titanium dioxide or Zn oxide. One class of this type of carbon nanomaterials, such as graphene oxide or fluorine, for example, fluorine can be in a spiral shape of dozens of hundreds of carbon atoms that they can produce drugs that will lead to cell death. Graphene oxide, we use graphene oxide for increasing the efficiency of PDT with methylene blue, and we just synthesize graphene oxide methylene blue nanocomposite and we publish it. We use it for PDT of human breast cancer cell, and we find that methylene blue in the form of graphene oxide nanocomposite is more effective than lone methylene blue. Other type of this class are quantum dot are nearly spherical fluorescent semiconductor nanoparticle with a diameter between 2 to 10 nanometer that denote the words as a platform for engineering drug delivery, and they have good surface modification, and this surface modification increases water solubility, biocompatibility, and target specific for them. As you can see here, according to their site, they have different colors. A quantum dot, for example, as an example here, quantum dot link with silicon phthalocyanin PS, and that there is a type of reaction, we call it BRET. The quantum dot as a donor can absorb a light in a short area like UV, and then after the FRET reaction, PS just act as acceptor and can be excited and produce singlet oxidation, which lead to oxidative stress on cancer cells. One of the important type of this class are upconversion nanoparticle, the luminescent material with triplet excitation states that emit light of higher energy, like this area, then exciting radiation by different mechanisms, including upconversion or simultaneous to photon absorption, and then change it to visible area, and PS can absorb it in visible area and finally produce singlet oxidation that lead to cell killing. In this extraction, there is transition metals such as lanthanide or actinic ions adapt into the solid state halves, as you can see here, record the attachment of an appropriate PS with an exciting bind matching the emission of nanoparticle. The common advantages of this type is when the PDT can not reach to the tumor several sites, and that they are several centimeters below the skin. So for reaching to this area, we can use this upconversion nanomaterial. In this slide, there is a schematic representation of energy transfer to photosynthesizer molecule from a nanomolecule such as upconversion, quantum dot, X-ray activated nanoparticle, graphene oxide. As I said, that depend of nanoparticle, they can be active with different light, for example, upconversion in red area, quantum dot in blue area, and so on. Another strategy for increasing PDT efficiency is combination therapy. In this regard, we have done different and several research, such as combination for the dynamic therapy against breast cancer cell line using methylene blue in combination with salicylic acid. We use photodynamic treatment in combination with doxorubicin against triple negative breast cancer, and we find that there is a synergy between photodynamic treatment and doxorubicin. Also, in type of antimicrobial PDT, we use rutin as flavonoid compound, and we just examined its effect on photodynamic inactivation against Pseudomonas aeruginosa and Staphylococcus aureus, and we found that when we use rutin, the efficiency of APDT mediated by methylene blue increased. Also, in another, experiment, we use combination PDT with rotoside for melanoma cancer cells. And in this study, we found that the obtained results show that methylene blue PDT plus rotoside have a better cytotoxic and antiproliferative effect against melanoma cancer cells. As you can see here, I show in this slide, we display that the alone PDT as a PS could act better on melanoma cancer cells, and also against gram-negative bacteria and gram-positive bacteria, as I said. We use for both bacterial study and also cancer treatment. We found that methylene blue and rotoside can interact with each other, and when the rotoside interact with methylene blue, the monomer form of methylene blue increase. That rutin or rotoside can stabilize the monomer form of methylene blue, which leads to higher PDT efficiency, because the active form of methylene blue is a monomer form. We find that when we use it rotoside before methylene blue mediated PDT, there is a higher cytotoxicity, so we selected this strategy. We examined this effect on melanoma cancer, so it's different. Experiment, cellular or biochemical experiment. As you can see here, all this experiment and display that apoptotic cell death increase in the form of combination of rotoside plus methylene blue, and cell death increase, and also colony forming ability decrease. We find that RAS production in the combination therapy increase. We had cell cycle arrays, and as schematic structure you can see here, the combination of PDT MB plus rotoside lead to RAS production, cell cycle array apoptotic, and colony forming inhibition. As I said, PDT has different application in clinic because there are several advantages, such as a single injection of drug follow after a certain time interval by single illumination, local rather than systemic treatment, a limited light penetration protect normal cell from photocytotoxicity, functional recovering without scarring, and can be repeated. As you can see here, PDT can use in different aspects, such as for skin problems, for for dental or oral problem. It has a very good effect. As in conclusion, I can say that photodynamic therapy is based on the possibility of the selective destruction of pathological tissue with accumulated photosynthesizer. Comparing to other therapeutic methods in oncology, PDT is distinguished by its selectivity by equivalent therapeutic result. As I said, combination of method with other techniques. In our research, we found that the side effect of doxorubicin decrease when it's combined with PDT. Considering the above aspect, photodynamic therapy is gaining more and more prominent position not only among clinicians but especially among patients. Thank you so much for your consideration. I like to thank organizing committee of this webinar for inviting me and give this opportunity to have a track in this great webinar.
Thank you so much, Dr. Khorsandi, for your valuable talk. Thank you for giving your precious time for making this webinar educational and informative. Ladies and gentlemen, as we have reached at the end of this event, and now we are closing the door on the lively and stimulating debate on photodynamic as an emerging tool in cancer treatment. I would like to cordially thank the management for organizing virtual scientific event that has gone live very successfully through YouTube and Zoom. Before ending this webinar, on behalf of the Applied Zoological Society of Pakistan, I would like to share home take message regarding World Cancer Day. Cancer is preventable. You have to improve your lifestyle and diet. Cancer is curable if detected early and treated promptly. Cancer can be treated at any stage. At the end, on the behalf of the organizing committee and our presenter, thank you for joining us today and have a very great day ahead. Stay connected and tuned with us for the AZSP upcoming events. Thank you.